Okay, this video is about standing waves and harmonics. And it's going to get us to or towards achieving the standard of being able to apply our knowledge of these standing waves to instruments to think about when frequency and pitch will change relating to Lab 3. It's a little tricky, so take your time and ask questions when things are confusing. So I'm not going to go through everything in the notes, but this one, so you should be reading through. This is a link to a Bozeman Science video that you should watch the beginning to get an idea of and familiarize yourself with these different harmonics or standing waves. So just as a reminder, the equations change depending on the standing wave. So the first harmonic, that is only half a wavelength. So we could say that the length is 1/2 a wavelength. Second harmonic, that is a wavelength. You see this part of the wave? Oops. Like it is just, there's a half and there's the other half. So we just say L equals the wavelength. Third harmonic, there's a half, another half. So we have 1 and another half. So 3 halves are 1.5. And then we keep going through. Now remember, when we're referring to L, that is just saying length of the string or tube or flute or whatever it may be, which in the example in the video is 2. Now, if we say that that length is 2 and then we try to use these equations to calculate the wavelength, we should start to see a pattern. So if the length is 2, that means L is going to be 2. Now I'm going to do this quickly and do a lot of it in my head to show you the pattern, but we can solve it using our algebra and the pink formulas as well. The calculated wavelength here, though, I need 2 of those 2's. I need 2 and I need 2 more. So 4. The next one, that 2 is a wavelength. 2. Next one is a little bit trickier, so let's maybe practice the algebra on this one. We can say L is 2, 3 divided by 2 wavelength. Now, I'm going to change this 3 divided by 2 to be 1.5. I'm going to divide. And then if I plug that into a calculator, 2 divided by 1.5 is 1.3. Now, if I also type in my calculator, 4 divided by 3, that's the same, right? And 4 was the original wavelength. Right, so for the first harmonic, the second harmonic is half. The third harmonic is a third. The fourth harmonic is a fourth. 1. The fifth harmonic is a fifth. The sixth harmonic is a sixth. So that's another way that we can solve these, is just take that original first or fundamental and divide it by the new number. But practice makes perfect. The more you do this, the more you'll see those trends. But something to notice and just a trend to maybe write is increasing in harmonic number leads to decreasing wavelength and increasing frequency. If we think about frequency, that is pitch. Increasing frequency, increasing pitch, higher notes. That's that versus the E. So in looking at your problem set, you really have one big example about this. And it's given you this information. It's saying we have this guitar string. It's tuned to a fundamental frequency of 440 hertz. And we have a length, not a wavelength, a length of 0.45 meters. We can use that to calculate many different things. Letter A you'll get from notes. But don't just write it from notes. Take your time. Draw them out. Write the formulas. Practice makes perfect on this, and it is confusing at the beginning. B is asking for the wavelength of the fundamental frequency. So I think to myself, fundamental frequency means first harmonic. I look in my notes, and my formula for the first harmonic is this one. So if L is 0.45, if we divide by 0.5 or times by 2, that would give me the same answer. I just need to double it, right? And if we think about manipulating this original formula, if I multiply both sides by 2, that would get rid of this and this, leaving wavelength equals 2L. So this is kind of another way to rewrite the fundamental. What is the speed of the wave on the string? Well, velocity is frequency times wavelength, number one equation of our unit. We want to solve for velocity. We know the wavelength is what we just solved for. And it tells me that this guitar string has been tuned to a frequency of 440 hertz. So at this point, I can say 0.9 times 440. Let's say it's 396 meters per second. Sound travels faster on strings than in air because they're more dense. Okay, now we think about, what about the second harmonic? What about the third harmonic? All of these, we're now changing harmonic, but we're not changing length. And we're assuming if we're not changing length, that we're going to keep the same speed of the wave. Now, there's many ways to do this, but let's just do it with our original formulas. So we first need to look and see for the second harmonic, what is the formula that you've written that compares length and wavelength? Well, it's the easy one. Length equals wavelength. So 0.45, the length of the string, equals your wavelength. Okay, that's easy. Now, if that's your wavelength, then let's think about what your frequency is going to be. Well, when wavelength goes down, frequency goes up. And if we think about how much, if wavelength is cut in half from 0.9 to 0.45, frequency is doubled. And so we can say that the frequency is 440 times 2. 880 hertz. Now, if you didn't like what I did there, just thinking about it conceptually, then you could use V equals frequency wavelength. And you could use 396 equals 0.45 times frequency. We would divide both sides by 0.45. And the frequency would equal 880 again. So whichever way you want to get there, it doesn't matter. Now we think about the third harmonic. Use those same equations and relationships. Your answer that you get should give you a wavelength of 0.3, should give you a frequency of 440. Think about that, 880, just receiving another 440. Or you can add them all up in the formulas. Velocity 396. Now, this is where it really starts to get fun, and this is really where your lab will get into. If I move my fingers on a guitar, I shorten the length of the string. How does the wavelength change? Now, if you think about this, we're kind of shortening the length, but honestly, it's more like we're adding a node where you put your fingers, a non-moving part. And so if I'm shortening that, I'm adding a node, I'm turning, say, I put my finger on the 12th fret right here. I am turning this harmonic, that harmonic can no longer be made because I'm adding a node here. I'm turning it to this one. So I'm increasing in my harmonic number. Which, how does the wavelength change? It decreases. How does the frequency change? It increases. And frequency and pitch are the same thing. Now take your time to kind of turn that into sentences and ask a partner to see if what you wrote makes sense. This stuff is hard and practice makes perfect. So pause, watch the video again, watch the videos on the notes again, and ask each other.